It was a time of great opportunity when it seemed anything was possible. And it was a time of the most terrifying threats, when ideas that many would now consider madness seemed normal. We will meet a missile whose capabilities seem unrealistic, a missile so dangerous that even its own creators feared it. Today on the horizon is a small engineering story of a great nuclear nightmare. The 1950s were a time of strategic uncertainty. It was clear that the primary weapon of the potential World War III would be nuclear, but it was not entirely clear what would be the primary delivery mechanism. The prospects of strategic aviation were becoming dim. The development of air defense, jet fighters, and surface-to-air missiles threatened to simply prevent bombers from reaching their targets. The new big trend, ballistic missiles, was still unclear. The models of the time were limited in range and lacked accuracy and reliability, and there was a widespread belief that a missile with a practically predetermined trajectory would be easy to shoot down. Amid this uncertainty, a third trend, intercontinental range cruise missiles, seemed promising. They were flexible in use and accurate compared to ballistic missiles, and also more simple and cheap than bombers. And so, in the mid-1950s, the military decided to take this trend to its peak. They wanted a missile capable of flying over 5,500 miles, at altitudes of a few hundred feet, below air defense radar range, and at speeds of Mach 3, or 3 times the speed of sound, at that altitude about 1,950 knots. This wish could have been the end of it. Intercontinental range at Mach 3 while flying above tree lines. Good luck. But it was the 1950s, and there were some brave souls, Convair, North American, and LTV. And sooner or later, they all ran into the same problem, a power plant that could give a missile/performance. The first step towards solving it was to use a ramjet. Unlike traditional turbojet engines, ramjet engines have a combustion chamber, and that's it. The airflow enters the intake duct at high speed, is compressed and heated by kinetic energy, ignited by fuel, and expelled, creating thrust. No compressors or turbines, the design couldn't be simpler. Furthermore, the lack of interfering elements allows the engine to operate at very high speeds, several Machs, no problem. But the ramjet didn't solve the fuel problem. Given the thrust and range this engine was supposed to provide, the amount of jet fuel it needed was immeasurable. And so, while discussing this problem, someone suggested, what if we replace the kerosene combustion chamber with a nuclear one? Indeed, why not? The 1950s were the era of true atom punk. Nuclear power was expected to be everywhere, from nuclear bombs of all sorts to power plants, ships, submarines, airplanes, trains, and cars. Naturally, when it came to cruise missiles, no one even hesitated. In 1957, at the military branch of the Lawrence Radiation Laboratory in Livermore, the Pluto project was initiated, with the goal of creating the Tory reactor, the heart of the future missile engine. And Tory promised to be a real breakthrough. Calculations showed that the reactor not only provided the necessary speed, but also radically solved the range problem. Just 50 kilograms of nuclear fuel was enough for supersonic flight over a distance of several 100,000 miles. The missile could circle the globe several times. But solving one problem gave rise to others. The system had to be compact and lightweight, yet powerful enough. Furthermore, being inside a ramjet engine at Mach 3 to 4 in a dense atmosphere at low altitude meant the reactor would have to operate under extreme loads and heat, a level that almost all materials available at the time simply couldn't withstand. But these were engineering problems, and engineers love solving problems. The first implementation of the project in 1957 was the reactor with the index Tory 2A, a scaled-down version of testing these solutions, including design and materials, infusible alloys, ceramics, and nuclear components adapted to new requirements. One of the solutions wasn't easy. Unlike environmentally friendly reactors with isolated coolant loops, the Tory was, so to speak, exposed to all winds. The coolant here was ambient air, which had to be heated. This was the only way to achieve the required power within the limited size and weight, but the cost was great. Yes, the jet stream from the nozzle was radioactive. It was decided to conduct the tests at the site in Nevada known as Area 401, rebuilt for this purpose. Despite all the difficulties, the program was implemented more or less successfully, and the nuclear scientists moved on to the next stage. This was the Tory 2C reactor, whose tests began in 1962, and was already considered a near-complete prototype. It was a cylinder 7 feet long and 4.75 feet in diameter, containing 465,000 fuel assemblies with 53 kilograms of enriched uranium-235, plus 26,000 air ducts. Yes, all this in a tube less than 1.5 meters in diameter. Its mass was about 6,000 pounds, 2.8 tons, very modest for a nuclear reactor. The test results were excellent. Power reached 461 megawatts, and the core heated to 1,242 degrees Celsius, like an entire power plant. Moreover, the results were not final, and were limited not by the reactor itself, but by the test rig. The compressed air supply for simulating supersonic flight was only sufficient for 5 minutes. Based on these tests, work began on the next reactor, the Tory 3, which was intended to power the serial missile. Development of the missile itself was in full swing by then. Engineers from LTV, Ling Tecmo Vought, creators of such renowned vehicles as the A-7 Corsair II attack aircraft and the ATACMS missile, were tasked with it. The project was simply called the Supersonic Low Altitude Missile, or SLAM. And the SLAM has become even more insane over the years. The military, seeing the potential of the new engine, wanted to create not just a cruise missile with a nuclear warhead, but in essence an unmanned bomber, capable of carrying multiple warheads. Taking all these ideas into account, the missile turned out to be quite unusual. It had a sharp nose and gradually widened to a diameter of 5 feet. Its overall length was 88 feet, almost the size of the B-29 bomber. Its mass was expected to be around 60,000 pounds, 27.5 tons. The missile's layout evolved during the design and testing process. The considered options included both a delta wing and a set of launch stabilizers. However, these would have had no dynamic surfaces. Control would have been provided by a trio of small rudders located in the nose. One of the main problems with supersonic flight in a dense atmosphere was the extreme heat. According to calculations, the airframe could heat up to 550 degrees Celsius, and it had to be made of materials that could withstand this. So, they decided to make the shell out of steel. Steel's advantage over aluminum, for example, was not only its great strength and infusibility, but also its low thermal conductivity, which could protect the missile's interior from overheating. Moreover, the steel was thick. In some sections it reached 6 millimeters, earning the missile a nickname Flying Crowbar. And the crowbar was precious. To further dissipate heat, the front section was to be coated with a layer of special gold alloy. The air intake layout also changed throughout the design's various iterations. Initially, it was planned to be circular with a central cone, like on the SR-71. However, after testing, a more exotic design was deemed optimal, an oval-shaped intake with 2 side scoops. This would reduce drag and simplify control. The air intake duct was positioned at the bottom, with a band that flowed into the fuselage near the tail, where the reactor was located. Air in the duct was decelerated and compressed, then passed through the reactor where it converted into a superheated gas, and was expelled through the nozzle at an enormous speed, generating thrust of approximately 38,200 pounds force. For context, this is the afterburner thrust of the Snecma Olympus engine from the Concorde. The monster J-58 from the SR-71 Blackbird was weaker. One of the benefits of the nuclear reactor was that the missile no longer required fuel tanks, and the freed up space was used for other instrumentation. SLAM received a weapons bay containing 2 rows of launch tubes, ranging from 14 to 26 in different iterations, each containing a hydrogen bomb with a yield of approximately 1.2 megatons. Its layout was similar to submarine missile compartments, as well as its destructive potential. The bomb release system was unusual. Instead of falling straight down, they were fired upward. Considering the carrier was flying low, this method allowed the bombs to explode at a higher altitude to increase their kill zone, and gave the missile time to escape this zone. After the weapons compartment come the compartments with equipment, control, communication, and navigation systems, including terrain contour matching. Drives of the rudders located here on the outside, and in the nose, a full set of sensors and antennas. Given that electronics are quite sensitive to temperature and radiation, all equipment had to be redesigned for these conditions. Additionally, to protect against reactor radiation and high temperatures, radiation shields and cooling systems were installed in the missile. The SLAM received an appropriate operational algorithm. The missile was to be launched from a platform using solid fuel boosters, like more or less all of its relatives. Other methods of takeoff were pointless, and the Ramjet engine doesn't work at low speeds. It would then fly to a patrol zone and circle there, at an altitude of about 32,000 feet and a speed of up to Mach 4. In this fuel-efficient mode, it would have a range of up to 98,000 miles and could remain airborne for a couple of days. Upon receiving the attack command, the missile would slow down to Mach 3, descend to 1,000 feet and fly along a predetermined route, attacking the designated targets one by one. After expending its ammunition, it was supposed to either ram another target, becoming a sort of dirty bomb, or continue flying over enemy territory. Here, the missile's non-eco-friendly nature acted as a weapon. Radioactive trail of its engine and the monstrous sonic boom of a large aircraft flying at low altitude at Mach 3. The SLAM could cause serious damage to entire areas simply by flying over them. The project was progressing well and was expected to reach the flight testing stage by 1967. But when the discussion turned to testing, a question arose. I pointed out that the SLAM, even without using weapons, caused serious environmental damage with noise and radiation emissions, both during flight and after the fall and destruction of the reactor. These factors would always be present. During a nuclear war, this wouldn't be so important. But how and where would it be tested and later launched in exercises if every use would have such consequences? And it was the 1960s. The public was already actively speaking out against nuclear testing and other radioactive games. So the SLAM, by simply appearing, could have caused political harm. There was also another problem: financial. The missile, according to initial plans, was supposed to cost about $5 million per unit. About $50 million today, which seemed attractive. But in reality, the SLAM and Pluto project turned out to be much more expensive than anticipated. Coupled with environmental and moral concerns, they were the subject of heated debate, and Congress began cutting funding, which slowed down the work. This was compounded by growing pressure from competitors, conceptual ones. Over the years of the SLAM development, ballistic missiles had evolved from clumsy monsters into fully fledged weapons with high reliability, accuracy, and intercontinental range. Moreover, it had already become clear that shooting down their warheads would be extremely difficult. Added to this was the emergence of a new class of carriers, ballistic missile submarines, which threatened to become the main component of the nuclear triad. Spoiler alert, they did. With these changes, the concept of strategic cruise missiles in general, and the SLAM in particular, began to seem downright useless. Ultimately, in the summer of 1964, 7 years after the launch, the Pentagon cancelled the SLAM and Pluto programs. The missile never materialized, nor did the Tory 3 reactor. The Tory 2C reactor was placed in storage and dismantled in 1976. Well, the demise of ambitious projects is usually described with sadness, but this time it's safe to say that the SLAM was never born, and thank God for that. Even considering the near-nuclear apocalypse of the 1960s, this thing was clearly too much, even for the most furious war dogs. Moreover, it left a positive legacy. Many technical solutions invented during the development of the missile and its reactor, in particular the materials, found application in aviation and nuclear energy. This was the best that the SLAM could have given the world. Subscribe to the channel to stay up to date with the nuclear story. There are still a lot of interesting things on the horizon.